Today, in Epi 204, I'd like to talk about effect modification, which I'm sure you've all heard about before. So now we want to go into a little bit of detail about how to do it and how to interpret the coefficients and what you need to do to make sure that they're giving you meaningful numbers. Okay? So to start with, remember that effect modification describes a scenario where the effect of your exposure, the magnitude of that effect, is different between, for example, men and women, between children and the elderly, etc. And it is not a bias. It doesn't mean that something's wrong. For example, if you do a study that only has children, that's fine, right? You don't have a biased effect estimate. It merely doesn't apply to the elderly. It's, in fact, very useful information when you can detect effect modification. So the basic rule is that confounding is your enemy, but effect modification is your friend. Now, let me just illustrate with some pictures an example of what I mean. In this case, we're talking about effect modification by a gene, and so I have some outcome, which geneticists use strange words for, and I have some exposure, and in this case, you see that the exposure response curve is different in the three different genotypes, but it's really the same. They're exactly the same. They're just shifted by the same amount at every exposure. So that means that the effect on the outcome is just the sum of the genotype effect plus the effect of exposure. So there's no interaction. Okay, so in this case, we are looking at the scenario where there is effect modification. So in one particular group of people, the slope of the line is 0. There's no effect of exposure. In another group, there's some effect. And in the third group, there's a bigger effect. Remember that your regression coefficient is delta y over delta x. It's the slope of the line. So this slope is steeper than that slope. That's what we mean by effect modification. So here's an example of that in the real world. This is from the Southern California Children's Study, where they recruited children in elementary school, and they followed them over time. They recruited them in different neighborhoods which had different levels of air pollution. Okay? And what they're looking at is exposure, in this case, to nitrogen dioxide, a substance that Volkswagen, is sometimes associated with, and asthma prevalence in the neighborhood where these people lived. Okay? And what they show is this is NADPH quinone oxide reductase gene, which detoxifies and prevents oxidative damage from certain kinds of foreign substances, and depending on which polymorphism you have, either nothing happens or the risk of asthma goes up with NO2. So this is an odds ratio of about 2 for the people at the highest levels. Okay? So that is effect modification. That's interesting. It's interesting because you look at this and you say, well, what does that do for a living, right? And that, whatever it is, it clearly has something to do with the pathway by which traffic pollution influences health. So you've now learned something about the pathway by which your exposure has its influence. Okay, so that was just an example of genes, which are popular these days, but there are plenty of other things that modify the effect of the exposures we study on our outcomes. So for example, chronic disease. People in Western countries live much longer than they used to, but that doesn't mean that they're not sick in some way for a large part of their life, right? We have people with diabetes, we have people with chronic obstructive pulmonary disease, we have people with obesity, which induces inflammation, systemic inflammation in the body, you know, and this is affecting a very large fraction of the population right now, etc. So there are many chronic diseases, and so, for example, this is a paper that I published in 2005 showing that diabetics are more susceptible to the effects of a heat wave. But of course, chronic disease isn't the only thing that matters. Psychosocial stress is very important. And no matter what those executives tell you about how tough their job is, it's the poor people who are subject to psychosocial stress, because not knowing whether the stockholders are going to be happy at the next meeting is different from not knowing whether you can afford both to take your kid to the pediatrician and buy food. And there are lots of studies suggesting that it affects health. And there are also studies that suggest it modifies various different exposures of interest in epidemiology. So for example, we did a study looking at the effect of lead on blood pressure. Well known that lead raises blood pressure in adults. It's not just for children anymore. But the effect was modified by psychosocial stress. And this was in the normative aging study, which you've taken a look at already. And this is not a low-income cohort. These people all had pretty reasonable jobs. But variations in stress, and that mattered. How do I do that, right? So in linear regression, it's straightforward. Let's say I want to look at whether lung function in the NHANES 2 data. Now, in the NHANES 2 data, lung function was obtained in children from age 8 to 18, I think. Started at age 8 because people are worried about how well you can get lung function measurements accurately out of younger children. And so lung function goes up with age in children because they're growing. 18-year-olds have bigger lungs than 8-year-olds, right? And so we would expect that there's a positive effect of age. There may be an effect of sex between boys and girls, of height, and then girls develop faster than boys. They go through puberty sooner. They hit their growth spurt sooner, on average, and therefore it seems pretty plausible that there's an interaction between age and sex, that the rate of growth of lung function in girls picks up sooner and then flattens out, stops growing sooner as well. So that's a way to test that hypothesis, and you can do that in the NHANES data that we've given you. Now, rate ratio models are a little different, and this has stimulated huge debates in the epidemiologic literature, which I think are arguing about angels on the head of the pin. There are different ways to look at it, and it doesn't mean that any of them are wrong. You just need to know what you're doing. So in principle, the model is the same. If I am looking at rates, then I would have a model where I would take a look at the rate ratio, and it might depend, for some outcome, it might depend on age, sex, and maybe there's an interaction, and that's what I want to test. I want to know, is B3 significant? If so, then the effect of age is different between males and females. That's effect modification. The complicating factor is that before you put in that interaction term, the model was already multiplicative. So let's leave out this B3 term and look at what we have, right? If I exponentiate this, I have the fact that the rate in the people I'm looking at, there's some baseline rate. That's what B naught is telling me about. There's an effect of age and an effect of sex. But remembering what we know about exponents, this is equal to this. So e to the b0, my baseline rate, the effect of age is multiplying that, and then the effect of sex is multiplying the effect of age on the baseline rate, and that's without an interaction term. So these relative risk or rate ratio models sort of have some built-in interactions. And what we're testing with B3 is there more than that? Is it even more of effect modification than we sort of built in our baseline model? And that's a fine question to ask. We just need to understand that it's a slightly different question than we were asking with the same term in a linear model. And the same thing is going to apply for a logistic regression, because that's more complicated even, but it's certainly got multiplicity in it as well. Okay? So some people say, well, you know, that's not really what I want to do. I would like to look at additive effects of age and sex on my baseline rate of some disease, and then test whether the effect of age, for example, differs between males and females. And so you might want to fit a model like this one. And in this case, if B3 is 0, there is no multiplicative effect. There's no effect modification. So this is a really nice model to fit. And unfortunately, this is an 8-week class where I'm trying to cover an awful lot of stuff, and this is a more complicated model, and of course, SAS, is not the most up-to-date statistical package in the world, and so I want to remind you that these models exist, but we're not going to have time to talk about them. So, what we do have time to talk about, and what I'm going to say to you repeatedly, is you need to center your data. Whenever you look at effect modification, you need to center your data. Why? Well, imagine I fit a model, and I'm looking at lung function. And my model is that lung function depends on age. Maybe it's a little lower in people who have asthma. Maybe it doesn't grow as fast in people who have asthma. And it depends on sex, right? So you would write in SAS, model FVC equals that. And then you'd put a semicolon. Okay, great. Now, what does that mean? Well, the coefficient of asthma in this model is the effect of asthma on lung function in males whose age is 0. Why? Because there's already an effect of age, right? and an interaction between age and asthma. So if I say that FVC is B0 plus B1 age, B2 asthma, and B3 the interaction, what is the effect of asthma on lung function? Well, suppose asthma is 1. Then FVC is B0 plus B1 age plus B2, because asthma is 1, plus B3 age, because again, asthma is 1, right? So in asthmatics, this is how lung function grows with age in asthmatics. It's B1 plus B3. That's the total effect of age. So what is B2? Well, if age equals 0, that goes away, and that goes away, and lung function is B0 plus B2. So B2 is the increment or decrement, depending on the sign, of lung function in asthmatics whose age is 0. What does that mean? Doesn't mean anything. So instead, suppose I center age. Now what I mean by that is for every subject in the NHANES survey, you subtract from their particular age the mean age in the entire population. Okay? Now, doing that does nothing to change the variation in age from one person to another, right? If one person is 16 and one person is 12, the difference in age is 4. If I subtract some constant from both of those numbers, the difference will still be 4. So the variation in age from person to person is the same, and so that won't change the coefficient of age, which is B1. It will change B0, but we don't care about B0, right? So that's cool. It doesn't do anything to change my coefficient for age. It still has the same meaning. Now, what happens if I look at age equals 0 with centered age? So that goes away, and that goes away, and I get B2 times whether or not you have physician-diagnosed asthma, and that is now interpretable as the increment or decrement compared to B0 in lung function for being an asthmatic at the average age. And that is interpretable. So I don't know what the average age is. Let's say it's 14, right? Okay, D2 tells you what's the effect of being an asthmatic on lung function if you're 14, not 0. Okay, so now all of my coefficients are interpretable, and that's a better deal. Now, the reason we're interested in this is that different people, in fact, respond differently to things. There's this huge interest in personalized medicine, right? How do I find out that different people respond differently to things? I need to look at effect modification. So, for example, there's this not terribly good drug for lowering blood pressure in the general population, which turns out to be much better in lowering blood pressure in African Americans, presumably because of some differences in genetics. That's useful to know. 20% of the population does not respond well to albuterol, right, which is the standard bronchodilator that we give to people? Well, if you're prescribing a bronchodilator to children, it might be interesting to know that and to know whether this particular child is in the 80% or the 20%. And if they're in the 20%, you need a different kind of bronchodilator. So besides understanding mechanisms of exposure, it's also useful for identifying people for differential treatment or for differential prevention. So that if I know, for example, that diabetics respond worse to heat waves than non-diabetics, I could target them to get them into air-conditioned places during heat waves as a public health preventive measure, and then they don't have the effect. Right? So that's why it's a good idea, but obviously power is limited. If I want to know whether diabetics respond differently and 10% of the population is diabetic, that doesn't give me so much power unless I have a large sample size. Okay? And for that reason, it's important to look at the size of the interaction and not just the p-value. If the effect on diabetics is 3 times as large as the effect on non-diabetics and the p-value is 0.1, but only 10% of the people in your cohort had diabetes, it's still worth mentioning that in your paper, because 3 times the effect is a big number. So we've already gone over that, so I'm going to now talk about an important issue in terms of how you identify whether there's effect modification. There are 2 alternative approaches that people use, and they're different, and they each have different advantages, and that's why it's a good idea to do both of them. So let me go over that. One is stratification. I fit one model in diabetics, looking at my exposure. I fit another model in non-diabetics. I get 2 different coefficients. So clearly, this approach has the disadvantage that only 10% of the people, say in my cohort, have diabetes, and so the coefficient in the diabetes subset is going to be noisier. Not only the coefficient of my exposure of interest, but the coefficient of all the confounders I'm controlling for. So there may be a little more noise in controlling for confounding because of this greater variability due to smaller sample size. So that's the bad news. The good news is if I fit a model where I regress outcome against my exposure and control for age and race and sex and body mass index and all the usual suspects, all of those variables can have different coefficients in the 2 different groups. There's nothing connecting the coefficients in the 2 groups. You're analyzing them separately. And so if you allow all of them to vary, you are capturing the possibility that your exposure isn't the only exposure that's modified by having diabetes. Maybe the effect of age is different in people with and without diabetes, right? So that's a good thing. On the other hand, some of the variation in those coefficients is just going to be noise, and that's the bad thing. So here's how you do that. So let's say I want to look at effect modification by sex. So I sort the data by sex in SAS, and then I run one of the Avogadro's number of regression procedures in SAS called GLM, which is designed to confuse you into thinking that it's a generalized linear model, which it isn't, and I run it by sex, so it's going to fit 2 regression models. And then I look at age and race and body mass index as predictors of lung function. in your data, say. Okay, and I get 2 coefficients for every variable for age, race, and body mass index. And I need to remember to tell SAS that, guess what, I want the regression coefficients. And I now have 2 sets of coefficients, one for the boys and one for the girls in this particular example, and great. And so if I want to know whether the effective body mass index is different between boys and girls, I can see that. Okay? So that's stratifying into 2 different data sets and analyzing them separately. Okay? But, you know, now I have beta BMI male, and I have beta BMI female, and I want to know, right, what's effect modification? Effect modification is that these are different. These are estimates, of course. How do I tell whether they're different? I got 2 different, they'll always be different, right? How do I tell whether they're significantly different? Well, there are ways to do that, right? But you need to do some things offline, right? You don't get that out of the output. Now, it is a common claim that we should reject the hypothesis that the slopes are the same only when the confidence intervals of the 2 betas don't overlap. So people will say, okay, here's the coefficient in males, and let's say here's the coefficient in females, right? Those aren't different because the confidence intervals overlap. What I really want to see to conclude that there's a difference is something like this, where the confidence intervals don't overlap. You see that all the time. The problem with that argument is there was an interesting paper published in 520 BC by Pythagoras that shows that it's wrong. So we've known that that's wrong for 2,500 years. Why? Well, okay, I have 2 coefficients, right? And I want to know, is the difference between those coefficients significantly different than 0, right? I want to know, do the confidence intervals of B1 minus B2 include 0? If it does, there's no significant difference between boys and girls. If it doesn't, there is. Well, it turns out that the variance of B1 minus B2 is equal to the variance of B1 plus the variance of B2 plus 2 times the covariance of B1, B2. That's the general formula for the variance of the sum or difference of 2 things. But B1 and B2 were estimated in entirely different data sets. So they can't have any covariance. So the variance of the difference is just the variance of B1 and the variance of B2. And so the standard error is the square root of the variance. So the standard error of this difference is just the square root of the standard error of B1 squared plus the standard error of B2 squared. And so the test of whether this is different than 0 is, does this plus or minus the standard errors include 0 or not? This is the confidence interval around the estimate. The confidence interval doesn't include 0. Then there is a difference. And the connection to Pythagoras, right, is that if I have a right triangle and one side is the standard error in boys and another side is the standard error in girls, then the hypotenuse is this, which is the standard error of the difference. And it's obvious that this is less than the sum of the length of the two sides, right? It has to be. And so saying the confidence intervals of the two estimates, which is just, plus or minus 2 times these standard errors, don't overlap, is saying that you want to have a confidence interval that is equal to beta 1 minus beta 2 plus or minus 1.96 times SE1 plus SE2, which is bigger than that, which is the right one. And so no, that's the wrong answer. Okay? Now the alternative approach, so you can do that easily. You get the two standard errors, right? You square them, you add that up, you take the square root, boom. No big deal. The advantage of doing interaction terms instead is you get a lot more power. You get a lot more power in the following scenario. You have a bunch of covariates, and you don't think all of them differ between boys and girls. Well, if that's true, then you're using the full data set for the full cohort to estimate the effect of these other covariates. You get more stable estimates of them, and so you should be able to, control for confounding by them better, and you have a bigger data set. And power depends on the size of your data set. So the alternative is then I just say I just put in an interaction term of BMI with sex. And the problem is, well, what if the effect of age is, as I claimed a couple of slides ago, different between boys and girls? I missed that. So I have confounding by the fact that, after all, 17-year-olds weigh more than 8-year-olds, and so their BMI may be different, right? And so there's an association between BMI and age that could confound the interaction term that I'm interested in. So the solution is do it both ways. So if I do it separately for boys and girls, I can look at the coefficients I get. I don't expect them to be identical, but if I see a noticeable difference in the coefficient of age between the regression in the boys and the regression in the girls, then I can come back here and add another term and redo the model in the full data set, which will give me more power to estimate this interaction, but control for the fact that maybe the effect of age also differs. Right? So by doing it both ways, I can figure out which additional interaction terms to put in, but take advantage of the greater power in doing the analysis in the full data set. So in SAS, I might, for example, look at a model where whether or not you die, so we're not looking at the children, right, depends on age and sex and some interaction term. So sex times age tests the hypothesis that the risk of death increases with age differently between men and women, right? So I would specify it this way in SAS, and if I now write out fully what the model that produces is, it says Y is B0, there's a coefficient of age, a coefficient of sex, an interaction term, and then some error term. So B1 is the effect of age in men, because we'll let sex equal 1 be women, and the effect of age in women is then B1 plus B3. Now this has a very nice feature, which is I don't have to square these standard errors and take their sum and take the square root and stuff like that to get a test of whether or not the effect of age is different in men and women in this particular example. Because the effect of age in men is B1 and in women is B1 plus B3, so B3 is the difference. It's the difference in the effect between men and women, not the effect in women. And therefore, the hypothesis test of B3 not being equal 0 is the test that the effect of age is significantly different in women. And so I so I get a coefficient and a standard error and a p-value for B3. That p-value is less than 0.05. Then the effect of age is different in women. So I automatically get the test of whether or not the difference is significant when I look at the full data set and look at the interaction. And so I get that, and I also get a confidence interval for the effect of age in men, because I get B1, I get a standard error, I can construct the confidence interval. But what's the confidence interval for the effect in women? Well, so the effect in women is B1 plus B3. I have a standard error for that, and I have a standard error for that. But now, these two coefficients are estimated in the same model, in the same population, so they do have a covariance. So, fine. The variance of B1 plus B3 is the variance of B1, the variance of B3, plus 2 times the covariance, and SAS will tell you what the covariance is. You can get that out of your proc GLM. Okay? So you then offline add these three numbers up, take the square root, and that's the standard error for the effect of age in women. So in this case, you immediately get out of the output whether the difference is significant, but you need to do an offline calculation to get the confidence interval in women. Now, if you aren't comfortable with hand calculators, if your cell phone somehow deleted that function, then there's a way out. You do this, right? That's what we've been talking about. Full data set, put in an interaction term. The p-value for B3 tells you whether or not there's significant effect modification. The standard error for B1 gives me the confidence intervals for the effect of age in males. But I could also create two new dummy variables. Male, which is 1 if you're a male and 0 if you're not, and female, which is the opposite, right? And then I could use PROC-GLM, for example, to fit this model, where I don't have a main effect of age. I just have the interaction term between age times male equals 1. So that gives me the coefficient of age for males. And this is 0 because if male equals 1, female equals 0, right? And 0 times anything is 0. But for females, this is 0. And this gives me the effect of age in females. And I only have to put in the dummy variable for male because female is 1 minus male. And so you only need one of those, right? And so that will directly give you the effective age in men, the effective age in women, and their standard errors, and therefore their confidence intervals. Okay? But it doesn't directly give you the p-value for whether B1 and B3 are different, which this does. So you run both regressions. And you get the p-value from here, and you get the confidence intervals from there. And then you don't have to figure out how to multiply or take the square root on your cell phone. And so to do that, you have to do a data step in SAS and create these additional variables, male and female, which you do that way. So let me show you an example. This is a study that I did with people in Switzerland, okay? We recruited 10,000 people in 8 communities in Switzerland. And we did lung function tests on all of them. And we did something called a methacholine challenge in all of them. So methacholine is a synthetic analog of histamine. And if you inhale it, it tends to produce a little constriction of the bronchi. If you're asthmatic, it's clearly going to produce a much more of a constriction. But the amount of constriction it produces, you know, is continuous. It's not like you get the same for all asthmatics. It's not like non-asthmatics. It's always 0, right? And so what we did is we calculated the percent decrease in lung function per unit dose of methacholine. We actually gave them multiple different doses of methacholine so we could calculate a slope for each person, right? And so this is the slope of their response, of their reduction in lung function from breathing methacholine per unit dose. That's on the y-axis. And this is how many cigarettes they smoke. And this was in the 90s, and people in Switzerland smoked a fair amount. There were a lot of smokers there. So this is what happens as a function of cigarettes per day. These are quartiles in men and women. And what you can see is that smokers are more responsive to methacholine. The more cigarettes per day you smoke, the twitchier your airways are, the easier it is to get them to shut down in response to another allergic stimulus. But there's a big difference between the response to tobacco in women and in men. Women had a much bigger response at the same number of cigarettes per day. So that's effect modification. So when you see that, has public health implications, right? You can put that into your education programs about smoking. You can target women, for example. And it also raises questions about why. What's the mechanism? And that helps further your mechanistic studies. Now, All of this is very nice and simple if everything in the world was linear. Unfortunately, that's not true. So now imagine I have an exposure and an outcome, and the relationship between them isn't linear. And then also imagine that there's a difference in exposure on average between men and women. The distribution is different, but there's no effect modification. Now, since one sex lives more at one end of the exposure range and the other lives more at a higher end of the exposure range, and the dose response with exposure isn't linear, it's a curve, then that will look like effect modification, right? So if, if the curve of response versus exposure looked like that, and women were mostly there, and men were mostly there, then the average slope for men, linear slope, is going to look like that, but the average linear slope for women is going to look like that. And you're going to say, men and women are responding differently. And the answer is no. They're just exposed differently. So you have to be very careful, because nonlinearity can look like interactions, can look like effect modification. Effect modification can look at like nonlinearity. And you need to try to distinguish those two phenomena. Okay? How could you do that? Well, hopefully there's a good range of exposure in both men and women. And if the dose-response relationship is really nonlinear, then it should be nonlinear in stratified analyses by gender. If I look at dose response in men and check to see if it's nonlinear, it'll indeed look nonlinear. When I look in women, it'll also look nonlinear. If that's true, then there's nonlinearity, and you need to control for it before you try to see whether it's different between men and women. If, on the other hand, it's linear in men and women but looks nonlinear overall, then really there is effect modification. So here's an example of that. This is that same thing, the slope of what percent decrease there is in lung function per unit dose of methacholine. And I'm looking at 4 different groups of people. Female current smokers, male current smokers, female never smokers, and male never smokers. So the females point up and the males point down. Okay? And smokers are filled in triangles, never smokers are open. You will notice that all the people with baseline lung function less than 3 liters are women. Well, all the people with baseline lung function more than 4 liters are men. If the relationship between response to this allergic irritant depends on how big your lungs are in a nonlinear way, and I look for a linear interaction, I'm going to find it. But if I look at this plot, which is by quartiles, right, I see that in fact everything seems to basically lie on the same curve, with the difference being that the black dots are basically all above the curve and the white triangles are basically all below the curve. So what this seems to be saying is there is an effect of smoking on methacholine responsiveness, but in terms of how methacholine responsiveness depends on baseline lung function, which is my exposure, it's all the same. And the reason why it looks steeper in females, remember, in females at any rate of smoking, the percent decrease is bigger than men. That's because this is a nonlinear curve, and women are there and men are there, and the slope, average slope, is steeper here than it is there. And that also makes biological sense, because the bigger your lung is, the bigger your bronchi are. If you have a bigger tube, a little bit of constriction of it is not going to matter as much as if you start with a smaller tube and constrict it. And so it's not surprising that the people with bigger tubes have less responsiveness to inhaling methacholine. But the key thing to understanding this is if I look at each of these four groups, so if I look at these male never smokers, right, that's this group, I see a curve like that. If I look at, I guess it goes up there. If I look at female never smokers, goes to there. There's some overlap, and those both look like the same curve. Now, nonlinearity can be confused, as I've said, with effect modification, but poor control for a confounder could also look like effect modification if you have different exposures, okay? So suppose that smoking in Switzerland, that women smoke less than men, and I didn't control for smoking. Then, since the men smoke more on average, there's more confounding by not controlling for that in the men than the women. And if I look at lung function versus age, I might see what looks like a difference that's really due to pack years, which I forgot to control for. Right? So that's another thing you need to pay attention to when you're looking for effect modification. Now, the last thing is that effect modification, we usually teach it to you where the modifier is a categorical variable. Men and women, diabetics and not. But effect modification can occur with a continuous variable as well. And so don't ignore that, and don't necessarily dichotomize them. So if x1 and x2 are continuous predictors of an outcome, you can still put in an interaction term. And now you say, okay, I could put it in the model. SAS will give me a B3. It'll tell me if it's significant. What the hell does this mean? How do I interpret that? Well, again, if I center my variables, x1 and x2, before I put them in, right, then I can say, so for example, if I look at temperature and humidity and their effect on mortality, say in a heat wave, I can say, well, at the average humidity, right, so I have B1 x1 plus B2 x2 plus B3 x1 x2. So at the average humidity, the effect of a 10-degree increase in temperature is something, right? And I'm at the average humidity, which is centered, so that something is just B1. But if the relative humidity goes up by 10% above its summertime mean, so now x2 isn't 0, then the effect of a 10-degree increase in temperature is going to be different. This is B1, and this is going to be B1 plus B3. So I can turn this into meaningful statements when I get these coefficients. Let me give you an example to show that this isn't just a theoretical concept, right? And most of you probably think that heat and humidity is sort of worse, so you probably do believe there could be an interaction. But if I look at the relative risk of current smoking on coronary heart disease, death, versus age, it looks like that. Because by the time you're 80, if you're still smoking, you're probably pretty resistant to smoke. Remember, it gets back to that differential susceptibility, right? Well, you would have died 30 years ago, right? So, but that's going to show up as a continuous change in the relative risk of smoking versus age. So this is a paper that I published in 1996. So you can see this has been around for a while, where I looked at a nonlinear continuous interaction between temperature and dew point temperature, to get back to that humidity and temperature thing, and hospital admissions for respiratory disease. So when it's cold, okay, you can see that as it warms up, again, those lines, as it warms up, the risk of hospital admission for pneumonia and other respiratory conditions is going down when it's also dry, right? But as I go to higher temperature, I start picking up the fact that risks go up. So in fact, a lot fewer people get admitted to the hospital for pneumonia in the summer and the winter, but the relative risk for temperature, if it's hot, more people get admitted. The people with pneumonia, small people, and a fraction of people with who have pneumonia then, it's harder to deal with when it's also very hot, and they're more likely to wind up in a hospital. But I also see, if I look this way, well, let me change the color. If I look this way, that as humidity goes up, I'm getting a kind of steep increase when it's cold. When it's warmer, the slope of those lines isn't as much. So I'm seeing an interaction. Humidity has a bigger impact when it's cold than when it's hot. Temperature increases are protective when it's cold, but eventually start to become a risk factor. So there's a sort of complicated interaction here. So those are examples of how you do analyses to look at effect modification. Okay, so I think we've gone over a bunch of stuff with effect modification, and that's it for today's lecture. Thank you.